In this video, we'll take a quick look at finite differences of polynomial functions. And this is kind of an interesting lesson because it will give us our first glimpse of how rate of change works with polynomial functions. So recall that the first differences of a linear function are equal. Now, what do we mean by that? Well, here's a linear function, y equals 5x minus 12, and we have a corresponding table of values. Notice that in this table, our x values are starting at 0 and increasing by 1 in each row. Let's take a look at what happens to our y values. From negative 12 to negative 7, we increased by 5. So we say we have a first difference here of 5. Similarly, from negative 7 to negative 2, that is once again an increase of 5. From negative 2 to 3, up 5 again. 3 to 8 is an increase of 5, and 8 to 13 is an increase of 5. So our first differences here are all 5. Now what does that mean? That means that we have a constant rate of change. Our y value is changing at a constant rate. Okay, every time x goes up by 1, our y value is going up by some constant value, and that value here is 5. Now what happens if we move on to a quadratic function? Well, here's an example of a quadratic function, y equals 3x squared minus 19x plus 12. Again, we have our table of values. X values are going up by 1, and let's take a look at what's happening to our y values here. From 12 to negative 4, that's a decrease of 16, so we'll write negative 16 for our first difference there. From negative 4 to negative 14, we have a decrease of 10. Negative 14 to negative 18, well, we went down 4 there. Negative 18 to negative 16, that's an increase of 2. And negative 16 to negative 8, that is an increase of 8. So our first differences are not equal for this quadratic function. So we do not have a constant rate of change here. But let's take a look at our second differences. That is the differences of the first differences. From negative 16 to negative 10, that is an increase of 6. Similarly, from negative 10 to negative 4, we went up 6. Negative 4 to 2, increase of 6 again, and 2 to 8 is an increase of 6. So our first differences were not equal, but our second differences are. Now this will always happen with a quadratic function, but let's think about what this means. If the second differences are equal, that means that the first differences must be linear. They can be modeled with a linear function. And that means that our quadratic function's rate of change is linear. Okay, so the rate of change of a quadratic function is linear. Let's move on and think about what would happen if our function was cubic, if it was a degree 3 polynomial function. Well, first of all, which differences do you think would be equal? Well, you probably guessed it right. The third differences will be equal. But let's look at this a little more closely. Here's a cubic polynomial function, y equals 5x cubed minus 7x squared plus 2x minus 4. We have our corresponding table of values once again. Let's take a look at our first differences. From negative 4 to negative 4, well, we didn't change at all, so our first difference is 0. We have 16, 62, 138, and 244. Those are the first differences. They are not equal, so we do not have a linear rate of change here for our cubic function. Let's look at our second differences. What do we get? 16, 46, 76, and 106. Once again, not equal, but we're predicting that the third differences will be equal. Let's see if that actually happens. From 16 to 46 is an increase of 30, 46 to 76, once again, an increase of 30, and 76 to 106, an increase of 30. So there it is. The third differences are equal, and this will always happen with a cubic polynomial. Now, what does this mean in terms of a rate of change? Well, if our third differences are equal, that means our second differences must be linear. They can be modeled with a linear function. And if our second differences are linear, that means our first differences must be quadratic. And that means that the rate of change for our cubic function is quadratic. The rate of change can be modeled using a quadratic function. And we can generalize here. In general, for a polynomial function of degree n, the nth differences are equal. So for example, for a degree 4 polynomial function, that is a quartic function, the fourth differences will be equal. For a quintic function, the fifth differences will be equal. And we can also talk about these things in terms of rate of change. So for example, for a quartic function, its rate of change will be cubic. It can be modeled with a cubic function. For a quintic function, the rate of change will be quartic. And as we move on in our investigation of rates of change, the reason behind this relationship will become apparent. We're going to look quite closely at it in future lessons. And before we wrap up here, I'll just leave you with one more thing to think about just for fun. And that is, in our last example, could we have predicted that the third differences would have a value of 30 just using the function's equation? In general, could we figure out what the constant difference for any polynomial function would end up being just using the equation? And the answer is we actually can. And I'll give you a hint. I won't tell you how to do it, but you're going to want to look at the degree of the polynomial and the leading coefficient. So I'm claiming that by looking at this 3 here, which is our degree, and our leading coefficient of 5, we could predict that the third differences would all be 30 for this function. Similarly, using our exponent of 2 here and our leading coefficient of 3, we can actually predict that the second differences will be 6. And you can do this for polynomial functions of any degree. So I challenge you to think about, how does that happen? What is the relationship? How can we predict what that constant difference will be? Have fun with that and take care.